The next function that I want to tell you about is f is going to map the complex numbers to the complex numbers given by f of z is square root of z. And what I have to do now is we're going to almost immediately see some of the details and some of the intricacies that we're going to have to deal with over the course of the semester. I need to tell you what is square root of z. And the way that I'm going to do that is if z has a polar form r e to the I theta, then we're going to define square root of z as the square root of r, so this is what's called the principal branch of the logarithm, times e to the I theta over 2. And here what I'm going to do is I'm going to let theta be any angle between pi and minus pi, not including the endpoints. Okay, so theta is going to be between pi and minus pi. And so what that means, and let's draw a picture, actually better than me drawing a picture. Let me show you a picture. So what's going to happen is these are what our outputs are going to look like. And again, this is the graph coloring method where each point kind of gets a color, and then you can see where the colors get mapped to. But what's going to happen is we're going to go from negative pi to pi. And so that means that we're going to go from negative pi, we're going to go from negative pi to pi. Okay, so around the circle that way. We do not include that endpoint. We don't include negative pi or pi. Okay, and there's some good technical reasons for that. Basically, it has to do with continuity. If you were to include either one of those points, you would have a sudden jump because even though the circle looks like it would be closed, you couldn't actually go over a path that way because you have to think about it. This goes back to the idea of a branch cut. And this is where this picture starts to make a little bit more sense that we had talked about at the beginning. If you kind of just cut off a horizontal section that's, say, 2 pi, then what's going to happen is that as soon as you cut it off, when you try and trace around the circle, you're going to have like a sudden fall off at some point. It's going to have a sudden jump discontinuity. And so to avoid that, just to avoid this issue in general, we're just going to delete that ray from the origin to negative infinity. So in other words, we're going to delete this part, doesn't get mapped to anything. And there's nothing special about deleting this part. You could actually take a branch cut anywhere you want. You just wouldn't be able to define the square root on that actual ray. So we're just going to go from negative pi to pi. And what we're going to do when we take a square root is we're going to take the square root of r, e to the I theta over 2. And so we're just going to take the square root of each of the things on the right. And so I could, by the way, I could equally define, I could put a minus there, and this would be an equally valid definition, but it would be a different definition. So just something to keep in mind there. And so this is what the square root is going to look like. So a few things just to say here. If squaring so if you were to take some graph, we'll come back to this picture in a second, but if you were to take some point and square it, we've already talked about the fact that that would double the angle, and then you would take the square root of the modulus of that complex number, and that's what your value would be. So it stands to reason that if you were to take the square root, this is kind of going from, this is kind of going the other way. What you would do is you would take half of the angle, which is consistent with what we have. So you would take half of that angle, and then you would take the square root of the modulus. And so that's why the square root of z is defined the way it is. Okay, so that's why it's defined that way. So that kind of undoes the geometric intuition of what happens when you square. And so if we were to take any number here, say some value near pi, when we take half of that angle, that's going to be somewhere near pi over 2. And so this is going to be, so of course we have 0, pi over 2 is our angle. So I'm talking about this angle 0. The angle, this angle here is pi over 2. If you were to go the negative direction, that would be negative pi over 2 because it's the other way. And so take any point that you want. Okay, so again, I was picking a point near pi. And when you take the square root, what's going to happen is that the modulus is going to get shrunk by the square root of the modulus. So it's going to be somewhere over here. Instead of being really large, it's going to be, square root of that distance. And then the angle gets cut in half. So whatever angle this is making, so you can think about kind of drawing this almost 180-degree angle, not quite, but it's almost pi radians. And then when you cut that in half, you get something a little bit less than pi over 2 radians, something like that. So that's kind of the intuition there with the square root. Notice that the way that we've defined the square root, if theta is between negative pi and pi, then the square root of z is only going to be between negative pi over 2 and pi over 2. So you're never going to have anything in the in that negative, in that half plane. Okay, so where the imaginary part of the real number is negative. Of course, 0 gets mapped to 0. This just wasn't included because this mesh probably looks a little bit complicated near the origin, but there's nothing wrong with plugging in 0 itself. You would just get 0. So the only thing that's not included is this negative, that negative line segment. Okay, and that's the square root of z.